All right. Happy Thursday. So thanks to everybody who made it out to the caves. I think we had a good time. We had a pretty good tour guide, so that was helpful, pretty knowledgeable at least. And then, of course, if you couldn't join us, either catch up with the alternative assignments. So again, either no travel, I'll just quickly write it. Oh, my pen isn't mapped either. Sorry. Now that they changed the podium setup in the other room that I lecture in, and so now my computer gets really confused hopping around. All right, so we'll call the no travel option, where again, you can write one paper on the cave, and then a second small paper, just a page on another formation. Or if you do travel, a lot of people mention they do the table rocks. And so you could take a little selfie there so I know you went, and just a page paper on that formation. All right, so now we'll spend a day lecturing. So like I mentioned, we'll just do a 2-hour lecture, so no quiz, and then we'll run makeup labs today as well. So I know a few people have told me you're doing makeup labs. So anything we need to do, come today if you can. All right, so now we kind of start. I feel like it's a little bit of our hodgepodge chapter. I feel like we're basically done with some of our major concepts. We've done equilibrium, right? We looked at it to death in all sorts of scenarios. We talked about Gibbs. And so now we're just kind of wrapping things up at the end these last few weeks here. Let's kind of again look at our syllabus, and we'll look at where this quarter is going to lead us. So we'll do radiochemistry today, so that's pretty brief, and then hopefully we'll get through some hydrocarbons. We'll go back to flavor of transition metal chemistry, so laying our foundations for higher level chemistry. And then we'll go back to OChem, again trying to get you ready for OChem if you're headed that path, or even if you're not, it's still good to know at least a little bit of basics. And then the last week, we'll wrap up kind of our organic chapter and transition to a taste of biochem and a little bit of polymers with that. So just kind of touching on our last bits of ideas basically for chemistry and everything to kind of prepare you for your future chemistry courses, hopefully. So let's look at radioactivity. And so this is just defined as the release of high energy particles and high energy electromagnetic radiation from the nucleus of an atom. And so again, this is it's kind of fascinating, this whole thing, because their half-life is established from kind of looking at a sample and trying to see how much material decays. Otherwise, this is just like a spontaneous process, right, that just kind of happens where it shoots out, right? So basically, there are atoms that eject particles from their nucleus. And I think I've kind of hinted at this before, we're not entirely sure why certain things are radioactive. It tends to be heavier analogs, especially as their protons and neutron numbers get kind of off, as I say it. And then I think we have a chart of the nucleotides in lab, or at least we should. I think the poster gets rotated around. But there are other sources where, again, you can kind of knock yourself out and look at all the different isotopes and why they are stable or what kind of decay they undergo. So again, most of that has to be studied. And then, so we define these nuclei that do undergo this spontaneous decay as being radioactive. And again, that just means that they decompose into smaller nuclei And as we've kind of hinted, different substances have different half-lives. And we will do our lab eventually. We'll go back to our radioactivity lab and quantify that. And so that's our radioactive decay process. Again, these nuclei are unstable. And then part of this radioactive decay also involves emitting particles in the form of energy. And so then this could go into like nuclear energy, which probably is gaining more popularity due to AI sucking up all the energy. So everybody forgot about global warming, I guess. But anyways, that went out the window. Not that it was really all about money to begin with. But anyways, everything's about money. And people were very scared of nuclear. But like I said, with people being so hungry for energy, that might shift. But anyways, we'll save the philosophical debate about energy for another day. So it is very energy dense as well. Oops, sorry. And then just a few definitions. So the parent nucleotide is the nucleus that is undergoing radioactive decay. And then our daughter is the resulting product. And then, right, sometimes that daughter could also be radioactive. And then you get a whole chain. And then nucleides with 84 or more protons are radioactive. And so then we'll look at our kind of main types of decay here. And I think we've looked at this before, but like I said, we're just kind of doing it again for depth's sake. And so we have kind of three main types of radiation. So we have our alpha particle emission, which is also helium. And then I don't know if you guys, are you guys aware of like the helium shortage potentially? And so from that, this is where like your source of much of the helium comes from, is from like radioactive decay. And then it is, I think, fractionally distilled, usually from fossil fuels. So right, that whole distillation process, that's usually where most chemicals come from and are separated from. And so that would obviously be super light, so go to the top of that distillation, fractionating distillation column. And again, we could go down that rabbit hole, or that's something, a good topic of like personal research is like, where does helium come from? And you can get into interesting things there. And then we'll look at beta decay. And so we'll kind of discuss this. So beta decay as defined here. So this is only referring to what I call it as negative beta decay. We'll go over both of that. But there is also technically what's called positive beta decay, or might also be known as a positron. So depending on your source, they may lump them all into one or separate categories. So just be aware of that. And then that would be the positive beta symbol decay versus the regular beta particle. And then this is our beta particle, as it lists here, is going to be, right, electron-like, if it's, again, just referring to the negative decay. Otherwise, we're just referring to a beta particle being something that's negligible mass there. And then we also have gamma rays, so this is a light energy. And so there's no like particle emitted, it's just kind of energy, but we'll see an example of that where basically something goes from an excited state to a less excited, more stable form and emits gamma rays, or it's emitted with something else. And so like I said, this one kind of lists it separately. as positron, but I'll just kind of relabel it again that this is just another name for positive beta decay. And then we'll look at one other process of this electron capture as well. All right, so here is our alpha decay. And so again, it's just the symbol for our nucleus. So of course, atomic number or number of protons on bottom formally, and then total mass on top. So right, matches with our helium. And then this is our typical reaction. So much of the helium comes from these different decay reactions. So one of them would be this conversion of 238 uranium, and it decays to thorium. And then, like I said, I think we've looked at this before, but I'll remind you of how we balance these equations right now. So all the numbers on bottom have to add up on both sides. So right, we started with 92, and then we ended up with a alpha particle. So then you could figure out that it was thorium, right? 90 minus 2 there. And then let me pull up our periodic table just so we're all on the same page. Oh, come on. P table. Did not pull it very fast. And then 92. So 92 down there with uranium. So, okay, that matches with our equation. And then again, balancing out our masses. So we started with 238 for our isotope of uranium. Then since we formed an alpha particle, so 238 minus 4, so 234 for the mass of that thorium isotope. And so again, right, much of the helium is from this process. I think also thorium-232 also decomposes in this way to give you alpha particles, but a lot of it is from this uranium. And then so looking at our alpha decay, so it's our most ionizing but also least penetrating type of radioactivity. And so your alpha particles can be blocked with a paper or light cloth. And so we'll, again, play with this in lab with our alpha, beta, and gamma sources. And just another reminder of how to balance it. So our atomic number decreases by 2, and our mass number decreases by 4. But again, nicely balanced with our chemical symbols. All right, so then we'll look at beta decay. And so then a beta particle is just an electron-like particle that is emitted from the nucleus when our neutron essentially splits. So in this case, looking at our negative beta decay, right, our neutron splits to become an electron and a proton essentially. And then if we kind of add everything back together, so our mass numbers, of course, beta decay, this is massless versus our proton. So 0 plus 1 gives us back the 1 for the neutron. And then negative for our, again, electron-like particle, so negative 1 there, versus our 1 plus proton. And again, right, add those two together, get back to 0 there. And then our beta particle is 10 times more penetrating than our alpha particle, but only half the ionizing ability. And then a heavy cloth or something would stop a beta particle. And so let's look at our equation. So it tells us, right, our atomic number increases by 1 and our mass number stays the same. But let's look at, so 1 is shown here, but let's rewrite this equation. And so this is for carbon 14. So if you remember, carbon 14 is radioactive, so it undergoes what I would call negative beta decay. And so then we can balance it and determine what our product would be. So 0 for the mass. So our mass number is still 14. And again, that's what our little hint set up here. And then, okay, well, we have a -1 here, and I need to get back to 6. So that makes our atomic number increase by 1, so 7. And then that gives us nitrogen. And again, that's our little cartoon representation here. So one of our, again, neutrons splitting, becoming a proton, and then that electron or beta particle being emitted there. So then try this example of what the product is. So this is another common example of a negative beta decay. Oops, that's supposed to be a 0. So determine the product really quickly. So just take a minute. So our phosphorus 32 is radioactive and gives us a beta particle. And what else? So what do we get for our product? What's the mass number? So 32. And then what's the atomic number? 16. So then that matches with sulfur. So good. So 32 sulfur there for the product. And then our last main example is this gamma emission. And so these are high energy photons. And so with gamma emission, there is no loss of particles. So no change in composition. So usually just a 0, 0, then gamma symbol. And so they're the least ionizing but have the most penetration. And so you'd want to protect yourself using lead or a thick cement wall. So I always kind of think of the movies, right? That's what everybody jumps in the fridge or whatever to protect yourself. Anyways, we won't talk about the residual radiation and all that, but and then so let's look at a few examples. And so these are a little strange. And so if it's not paired with like another reaction, sometimes you might just see, so this is the most common example, and it has this little symbol here. So it's this technetium atom, and it has this little M, and that tells you that it's metastable. And so that's like really your only hint. And then it's kind of strange because it just goes to another form of it. So it's still 43 technetium, and you can tell I never work with this element anyways. Well, that goes down another rabbit hole. It's actually really hard to work with like radioactive elements because, I mean, obviously they're kind of dangerous in the sense that they obviously emit radiation, but that leads to a lot of regulation, and you have to wear a monitor at all times, and blah blah blah. And so that unfortunately has like shut down a lot of research, like the labs that even like used to do it historically, like at the university research level, it just becomes like too prohibitive. And again, you could debate the ethics of that and the effect on research, good and bad, but yeah, essentially. And like I like don't fully like understand kind of what's going on, but like usually it's coupled with other like radiation though. All right, so let's look at some more examples. So now we'll look at the positron emission, which again could just be lumped in with beta decay, but now we'll just call this positive beta decay. And so it has a charge of 1 plus, but a negligible mass, so sometimes referred to as the anti-electron, so mass of the electron, but opposite charge. And then it would follow the beta particles in ionizing and penetrating ability. And so this is one of our examples of this, where your 30 phosphorus decays to 30 silicon, and then you can balance that out, right? So now we have a plus sign, so our mass atomic number goes down, then mass stays the same. And then our last example is electron capture. And so sometimes an electron is pulled into the nucleus and combines with a proton, and that would make a neutron. So there's no particle emitted, but our atom still changes since our proton, right, combines to make a neutron. So our mass will be the same, but then our atomic number decreases by 1. And in retrospect, so I might go run during the break to print this. So this was our cheat sheets. We have more kind of examples. Some of them we've gone through. But here's right another different one. So our beta emission. So now with 228 radon going to actinium here. There's again the high energy state, only indicated by that meta stable. And then here's the last one that we didn't look at. So our electron capture, the kind of classic example of that is this ruthenium-92, pulls in an electron to make then our 43 technetium element. All right, so we're already doing this I think we've done this before, but like I said, good to make sure everybody's on the same page, especially with people doing a little bit of switching sections. And so like we already saw, these nuclear equations are pretty useful for balancing. So like we saw, the sum of our atomic numbers has to be equal. Same with the sum of our mass numbers. And so you could also be given a word problem, right? Like 238 uranium undergoes alpha decay. What's the other product? And then that's how you could determine it was 234 thorium there. So let's try another one. And so let's do that. And this time I'll just tell you 222 radon undergoes alpha decay. So see if you can write out the equation. on an exam, I would tell you if there were like more equivalents of alpha decay, by the way, like, oh, it produces 2 or 3 equivalents. And so in this case, it's just 1. So then writing out our equation. So then what's our daughter isotope? And watching the chat too, but what do we get? So polonium, and then what's the mass on polonium? So 218. So good. And I don't know if anybody. Ooh, that scared me. I don't know if anybody's done any like radon testing before, or if anybody even has a basement. So remember, radon is one of those gases, right? And so I don't know if y'all have basements or not here in Medford, or I know my house actually has a basement. No, and I haven't done radon testing. I don't know if I should. But that is a common exposure for people is their basement, since right radon is again going to be closer to the earth, and so any like sort of off gassing would come from this and some sort of exposure. And I mean, I couldn't find Medford stats. I was trying to look real quick. Well, it does say that certain zip codes in Medford may have high levels. Well, now I have to investigate it, but yeah, I was just kind of curious. But it is something to maybe look into. Could lead to lung cancer potentially. Anyways, let's do another one. So a lot of alpha decay examples. So let's try another alpha decay. And so I'll say 172. Let's change my color a little. So 172 gold undergoes alpha decay. So what would those products be? All right, so what's our daughter isotope for the 72 gold? So iridium, and then what's our mass number? 168. Sounds good there. All right, so those aren't too bad. And then this should look familiar, right? Our rate laws, I think that's why we touched on this earlier. And then I just bring it back to point out that if we're going to work with any half-life equations again, that we're going to use this set of equations, right? Our half-life expression and first order. So this is our general equation. So we'll probably look at some practice problems, or we'll also kind of look at our brute force method, as I call it. And so let's look at our other bit from this chapter. And so that's our mass defect. And so now this is telling us kind of where our energy comes from. And so our mass defect is defined as the difference in mass between the nucleus of an atom and the sum of our separated nucleons. All right, well, let's take a look at what this means. And so now we also need this equation. So E equals mc squared. And so this is our setup. And basically, right, let's look at bismuth. So bismuth 209. So its mass, again, properly is 208.9804 AMU. And okay, so let's figure out our mass defect. And so the way this works is, well, if we were to get this appropriate isotope, so that would be 83 protons. And so the mass of one proton is 1.007825 AMU. And then it would have 126 neutrons. And a neutron mass is 1.008665 AMU. So let's see what it should have a mass of. Once I pull up my calculator. All right, so let's add that up. Oh no. So then we should have a mass of 210.741265 AMU. And okay, so there's our mass defect. So let's write this out for a second. So 210.741265 AMU. And so then we can get our difference in mass then. And so now I'll just do that. So our 210 so minus the actual mass. So a difference of 1.760865 AMU. And so now I'm going to jump units on you guys. And so kind of the units that's used is the C squared becomes 391.5 mega electron volts. So kind of, right, we could go back and like derive units later. So remember, this was a joule. So I just have this direct conversion in my notes. And so that means that we can plug this in for our E equals mc squared. And right, we can plug AMU for our mass in, so that's also why I'm in this mega electron volt units. And so then we can calculate our energy. So 931.5 mega electron volts times our mass defect. Oops, sorry, switch those. And so then this gives us 1,640 mega electron volts. And then we want to convert this like per nucleon to kind of see how much is, again, kind of stored in each binding energy, right? So basically what we're figuring out is some of this is lost to our binding energy, right? Our missing mass is what ends up holding everything together. And so then we can divide this by our total number of nucleons. So that would be divided by 209. And so then we get about 7.84 mega electron volts per nucleon. So that's kind of a cool calculation as well. Okay, let's look at some other half-life equations. So let's try this one. So this one it'll be a little easier one. And so I'll say, yes, you could use an equation, but maybe you could also just kind of figure it out. So let's try it. So I think I have 131 iodine has a half-life of 8 days. And so if I have, let's say I have 100 grams, how many grams will remain after 32 days? And so what's kind of an maybe easier way to do this problem than busting out all our equations? What can we kind of brute force? What does this half-life mean? How many half-lives have passed in this problem? So 4 half-lives. And so we could just brute force it. So right, we always have our equations, but some of these are easier to set up with just our kind of parent and then number of half-lives. And then I try to make it even easier by doing 100 grams. So okay, 100 grams, and that's to start off with. And then yeah, we determine, okay, well we went through 4 half-lives in this problem. So then at 50 grams, it's 1 half-life, 25, 2 half-lives, 12.5, 3, and then 6.25 after 4. So then we could stop here, and then that's our answer, that we would have 6.25 grams left. Or we could have done this as a percentage. So right, it would have been 6.25% multiplied by original amount, but all right, good. So let's try a slightly different variation of this problem. And so let's say we're looking at carbon 14, which has a half-life. Oops, sorry, misspelled life completely. Half-life of 5,730 years. And let's say we had 5 milligrams of material, and now it is 1.25 milligrams of material. So how much time has passed? So do we get answers in here? And chat, let me know how you got the answer. I was kind of curious. So there's an answer in the chat. We could, plug it into, again, some of our equations. But this could be another easy one to kind of brute force. Maybe you start sketching it out. Again, parent versus half-lives. So then we started off with 5 milligrams at our initial, and then half that, so 2.5 milligrams after 1, and then 1.25 milligrams. So we're already there, so that wasn't too far. And so that's 2 half-lives, So then we can tell, okay, well, this was 5,730, and then this was another 5,730, which gave you 11,460 years. And so you could still use your equation of our t is equal to 0.693 over k, and then plug in our t half-life, and then put it into our equation. So we could still do that, but like I said, we'll probably see some easier ones kind of in this exam that kind of are more tailored to what I call the brute force method, so kind of see it both ways. And then so with the formula, so I think people want to see the formula. So we could set up our half-life, so 5,730 is equal to 0.693 over k. So solve for that. So then we have our k, so then we want to solve for this. And then we'll take natural log of AT. So then it would be 1.25 over 5 equals negative KT. And so now plugging in, so natural log 1.25 divided by 5 and divided by our k. And so I think did I do something wrong? Oh, because I didn't do, okay. One more time. 1.25 divided by 5, sorry, I always skip something. Divided by 1.2029 times 10 to the negative 4th. And so that does give us about the same answer. So with the negative sign, so 11,466 there, which is about what we get. So whatever method you prefer, formula or brute forcing, but like I said, trying to get you to see kind of both of them so you can use whatever's easier, or depending on your situation, if the numbers are easy enough, maybe you just brute force it. All right, this is a good spot for a break. I assume people want kind of the this thing maybe printed out as a cheat sheet. Okay, so I see some yeses. So I'll get that printed out. I'll get it in color too, I think. I'll leave this up, and then we'll switch gears to kind of O-chemy. Oh yeah, and do let me know about makeups. I know a few people have talked to me, but just double, triple check, make sure that we have everything so our wonderful stockroom helpers can get everything ready for y'all. All right, I think we're still missing a few people, but all right, I fixed the notes by the way, so they should be updating. So now let's switch to our OChem chapter. And so now we're looking at kind of like organic molecules and just starting again kind of simply with this just so that we have a foundation for OChem. And I know, not everybody's going on to OChem, but it's at least good enough to get some sort of basis. All right, so we start off with our alkanes. And so an alkane just means it is an organic that has carbon and hydrogens only, and no double or triple bonds. And this is also sometimes referred to as being fully saturated. And again, all that means is it has all hydrogens on it. And so it could be something, and so we want to get used to the organic abbreviation. So I could draw something like that. 1, 2, 3, 4, 5, 6, 7 carbons. And we'll get into the naming, but this could be heptane. And this would be a CH3. And now you're filling in your brain that everywhere where carbon only looks like it has 2 bonds or so would be filled with hydrogens. And so then we have, more specifically, are what's called acyclic alkanes. So then this would just be like we drawn above. So straight, chain, or branched. And we'll get into the branching, but it could kind of go off in any direction, just as long as we have only 4 bonds to carbon. And then all of these acyclic alkanes follow this general formula of Cn and then H 2n plus 2. And so we could see this for like heptane here. So I had done, so heptane was C7, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So C7H16, which follows with that formula. So 7 times 2 is 14 plus 2 is 16. So there's our standard alkane formula here. And then we could look at our saturated hydrocarbons. Let's move this over. So this is how to name our saturated hydrocarbons with these prefixes. And so y'all probably remember like methane, right? CH4. So our simplest hydrocarbon. And then ethane, would be 2. And ethane you could even draw as just a little line like so. So that'd be 2 carbons. And then propane. Oh, so sorry. I didn't do a good job of following my own notes. So methane, ethane. And so ethane, I forgot my organic kit. So I'll have to bring in my baby organic kit for you guys. And so again, with OCHEM, we always kind of want to think about where everything is spatially. And so right now I'm drawing kind of the most energetically favorable, what's called conformation of ethane. And if I had my model, this would make more sense. Yeah, so they're all tetrahedral. And then I was trying to show, so basically, right, you want to remember that a single bond has rotation all the way around, which is why, again, I should have grabbed my kit, but I forgot. And then this is something that you'll do, like I said, in OCHEM. And it's just about the position of these hydrogens. And sorry, I want to find, I saw it, this is what I was looking for. This shows up on like every OCHEM exam in the history of OCHEM, usually first quarter, but just going through the energies of rotation, excuse me. And sometimes you look at this dichloroethane, so as you can imagine, the two chlorines across from each other is like super, super unfavorable as they are larger. And so usually there's an exam question in OCHEM, either, like I said, with chloroethane or ethane, and drawing this or something. There's always something with this. But how I was trying to draw it was in the most favorable, and I wrote this wrong, eclipsed staggered conformation. This is not eclipsed. I wrote the wrong thing. So this is staggered, sorry, where they are far apart. But again, just kind of something to keep in the back of your mind with OCHEM. That was like, okay, we have 3D. And like that's the number one emphasis I can say about OCHEM is like you have to think in 3D. And then so propane, we start getting into a few interesting things now. So now we have a few isomers. So we can have our straight chain propane. So 1, 2, 3. And then, I'm trying to think if there's any other ways to write that. So, yeah, sorry. No isomers for propane yet. So C3H8. But now butane, we get into a few isomers. So we can have N-butane, which is our straight chain butane. So 1, 2, 3, 4. Or isobutane. So isobutane would have this group here. So 1, 2, 3, then 4. So that would be isobutane. And so same formula, right? So still C4, H10. Don't forget the little hydrogen there. And CH3, CH3. Obviously a carbon in the center, CH3. So there's our 10 hydrogens here. And so then we start getting into at least our definition of structural isomers. And there are a lot of structural isomers in OCHEM, as you'll quickly discover. But it's anything with the same chemical formula, but different connectivity. And I believe we've already seen this somewhat in our esters versus alcohols. So they would have the same formula. So right, we could look at this. So this is C2, H6O. But again, this is an ether, right, versus still C2H6, right? 1, 2, 3, 4, 5, 6. But the way that this is written, it doesn't show that this is an alcohol, right, versus the ether. Which gets into, I think, right, you guys' frustration sometimes where, like this could be written like C2, CH3, C2OH, right? And sometimes they write it all out to emphasize, no, this is the alcohol versus, I mean, they might just write it like this anyways. I'm not sure you really, I mean, they could do something like that, maybe to emphasize that it's an ether, but again, that gets into like all sorts of inconsistencies in chemistry, but you kind of see why. Like it depends if they're like trying to emphasize a certain group or not, or if they're just giving you the formula. And then like once you get on to OChem, you'll be doing puzzles and stuff anyways, where you barely have a formula. And then we want to look at some reactions. So of course, we remember our combustion reaction, right? We quantified that in this class. So we had our general CXHY, potentially oxygen-containing compound, and then that always gave us CO2 and water. We could balance it, right? We've seen propane, and that reacts with 5 equivalents of oxygen to give us 3 of CO2, 4 of water. But we've kind of, like I said, we've kind of been there, done that. And then we can do other reactions with these alkanes. And so this is a substitution reaction. And so this UV light, sometimes, so usually if you have a UV, this is a good hint that it's a radical mechanism. So usually the UV light is used to kick off some sort of radical. And so that's how it initiates. So we have our chlorine gas, then we hit it with UV, and so then that splits this bond to create the chlorine radical, which then goes on to kick off, right, one of our hydrogens, make HCl, and then make chloroform in this reaction. So again, just substituting out one of our hydrogens. And then let's just say, well, let's do a quick review, I guess. So now I want to say, like, don't forget about our hybridization. So again, we've kind of been there, done that, but let's remind ourselves. So we had sp hybridization, like we've seen in CO, and maybe you want to draw out kind of your shape there. So sp hybridized with our 2 lobes. Then we had sp2, and we've seen some examples of that. So of course we have our CO double bond, kind of these general molecules, right? Acetone, or so ketones. We'll look at other carboxylic acid derivatives, right? Or don't forget about graphite, or anything else that's sp2, like benzene. So I'll draw out benzene. Or any other, right, benzene derivatives. And so again, they're all flat, right? So we have to think in 3D for OChem. So okay, we're thinking these are flat, they're flat. So that when we're looking at the reactivity, we'll know whether there are possible isomers or not. And then sp3, so we'll stop at sp3 because we're mainly carbon focused right now. And so I'll just draw out methane. But okay, we're just always thinking, right, 3D structure, which I think you guys have been doing a pretty good job at this and seeing all this, but it's just continuing to practice and put everything together. All right, so then this leads us to our functional groups. And so we may have seen some, but again, we're just like putting everything together, building up our OChem vocabulary now. So we have our methyl group for CH3, ethyl for 2 carbons. So notice propyl is when we have a straight chain attachment versus isopropyl. And so I always think of isopropanol. So isopropanol, which we'll get into the naming, but we're seeing, okay, isopropyl group, and then our nol for our alcohol, but like I said, we'll go over that. And then we have fluoro, chloro, bromo, iodo groups, these amine or amino groups, so we've kind of started to touch on those in our class. Nitro groups, so we generally don't work with them in Gen Chem, but you might do some nitro groups in OChem. Usually a traditional OChem lab is some sort of horrible azo dye. And these azo dyes usually have nitro groups on them. I'm trying to find. They're also very brightly colored. Of course, now I can't find a good example. Oh, I'll find an example later. Then we have our phenyl ring. And so that's any kind of benzene base ring. We'll look at like, so toluene is another common solvent. So benzene with a methyl group on it. All right, so now we'll try to take a stab at some naming. And so this is for our alkane nomenclature. And so first you'll have to find the longest chain, which could be easier said than done. And so this is often too where like young O-chemists start to mess up because, right, it doesn't matter which way the chain is going. So sometimes you can draw something deceptively and that's not actually the longest chain. So you kind of have to go around and count. And so that's my second greatest advice for OChem is like count your carbons and then count again. And so that's the first hardest thing is like which truly is your longest chain. You may have to check out several mappings. And then we'll look at our groups attached to that chain. Then we'll number them starting basically nearest a substituent group. So you're trying to give your group's highest priority, and we'll look at what that means. So we'll have our number, and then we can list the groups in alphabetical order and use our di, tri, and tetra to show groups of the same kind. But like I said, we'll practice and get to that. And so let's take maybe like 5 minutes and see if you can draw out your isomers of heptane. And so there are 9 isomers of heptane, so you don't have to name them yet, at least, because that might be difficult since we haven't practiced. But can you at least draw them? So different connectivities. Obviously the straight chain and heptane is already drawn out, but how else can you rearrange and connect them? And watch out for drawing like the same thing. So I'll give you guys a bit of time to stew on that. So I do want to keep it moving for the interest of time since I'm trying to cram all of OCHEM, but I did want to go back to these nitroanilines that I'd mentioned, since, like I said, they're using azodye synthesis a lot of the time. And so these nitro groups tend to make the compound like colored. So there's a lot of synthesis using like 4-nitroaniline or any sort of substituted aniline, and we'll kind of see where the 4 comes from in a second. I couldn't find a good, I wanted a picture of the product, of the azodye itself, but I was having issues finding it. So maybe I'll look that up later. But azodye just refers to this nitrogen-nitrogen double bond there. And then we can see our nitro group still hanging on. And this gives it a lot of conjugation and color. And we could actually do this one in our lab, I believe, if we were so inclined. So we're going to do a synthesis of aspirin. And so this is one of our starting materials, or is our salicylic salicylic acid, excuse me. So we could do this, right? Pair it with 4-nitroaniline if we had it, or right, just order it, and then pretty simple synthesis. Anyways, won't go down that rabbit hole. So how are we doing with our isomers? So we'll start with 1, 2, 3, 4, 5, 6, 7. So this is N-heptane. So N just referring to straight chain. Now, what other permutations, combinations can we do? And I don't know if anybody wants to run to the board in class or try to describe what you did. You could try to think of how to tackle this too, right? Because you have your heptane, and then I would ask, well, let's start with our hexanes then. So how many hexane versions can we make? Anybody put a methyl group? Oh, what did you say? So where'd you put your methyl? Perfect. So, and then just count and triple count. So 1, 2, 3, 4, 5, 6. So 1 on the second carbon. So good. So that would be, again, we would find our longest chain as hexane, and then we have a methyl group. And so this is what they mean by like assigned priority. So we wouldn't label it 1, 2, 3, 4, 5, 6, because that would give this a 6 priority. And if you wrote it in the 6, right, or in the 5th position, no, it's the same, right? And so we want to do high priority, aka give our group the highest number. So we should label it 1, 2, 3, 4, 5, 6. So then our proper IUPAC name is 2-methyl, again for our position, then our group, and now hexane. Good. And then, so where did you put the other methyl group for your other hexane permutation? Perfect. 1, 2, 3, 4, 5, 6. So 1, 2, 3, methyl hexane. And again, right, this is our only option. You could put it on this carbon, but that's still 1, 2, 3 methyl hexane then, right? So you make the same thing. So good. All right, so what about, let's now think about the next number. So what about pentane? What are some permutations, combinations on this one? So 2 and 4, so good. So 1, 2, 3, 4, 5. Oops. Oh my gosh, I just can't draw a straight line. And then 2 and 4. So that looks good. So then we have 2, 4, and then this is where we can use our prefixes to say dimethyl to show that you have 2 methyl groups, and again they're at the 2 and the 4 carbons. So 2,4-dimethyl pentane. And then I think there's at least two other, no, there's several pentane permutations, sorry. So what else could you do with pentane? So 2, 3. So good. What else could we do? Like a ethyl group? So let's look at that, because it has to only go, it can only go on the middle one. And so we could take a look at like Y for a second. So right, we can't do this one. So 1, 2, 3, 4, 5, 1, 2, because that goes back to the longest chain. So then that's 1, 2, 3, 4, 5, 6. So this one is a hexane isomer, which is, again, why these can be kind of tricky. But this one is valid that we've drawn. So I'll go, eh. So that's really 1, 2, 3 methyl hexane again. But this one works like you were saying. So this is our longest chain. So 1, 2, 3, 4, 5, right? 1, 2, 3. Let me Just redrawing this prettier. There we go. And right, this is still 1, 2, 3, 4, 5. So longest chain either way gives us 3 ethyl pentane. Okay, there's still more pentane permutations kind of building off of these. What else could we do with this methyl group? So I'll give you a hint. We could stick them on the same carbon. Again, if I could draw it's like slightly better. So we could have 2,2-dimethylpentane. And then just be careful. Somebody suggested 3,4, but that'd be the same as 2,3 if you just rearrange the priorities. So the last two pentane isomers are 2,2 and then 3,3-dimethylpentane. Once I write them. 1, 2, 3, 4, 5. There we go. So I think those are our pentanes. And now I think we're just missing one, right? So there are 9 of them. So 1, 2, 3, 4, 5, 6, 7, 8. So there's a butane isomer. If anybody can guess it. So 2, I think we just need another methyl group. So 2, 2, 3, trimethylbutane. You were pretty close. You're the only one that gave it a stab too, so. Everybody else is chilling. But yeah, so now putting 2 there, 1 there, and then I don't think we can draw anything else. Everything will come out the same, but good. So 2, 2, 3, trimethylbutane for the last one. All right, let's see what we can keep going through. So then we have our alkenes now with our E. And so this implies any sort of double bond. And so we could have something simple like this, right? Ethene. And again, right, you're thinking 3D. So this is going to be a flat structure here. sp2 hybridized, whatever you need to remember. And then same thing, we can name and give our position. So now let's look at butene. So 1, 2, 3, 4, but this would be, so assigning priority, this is 1. So this would be 1 butene, so but for 4, and then write the 1 indicating the position of our double bond. Or let's say we moved it, so 1, 2, so now I put my double bond there, so that's 2 butene. And did I lose my label? And then we also want to look at our cis and trans isomers here. And so, again, the whole point of that double bond, I mean, maybe we would want to go back right to our hybridization chapter, beginning of like 222. And remember that we said that we have this pi bond. So right, this is from our pi bond, kind of through space interaction is what's giving us that double bond. And so the whole point of this double bond and showing all this is that our cis and trans isomers are not easily interchangeable. Right, there is some barrier to rotation. Perhaps if you heated up some of these compounds, you might be able to go from the cis to the trans isomer, but that's right not easily done because again, right, we would be breaking a pi bond or would need to temporarily, right? So we can't just rotate between the two. And so then we have looking at butene again. So then we could have our trans isomer, where they're kind of on our opposite sides here, and also known as E, versus our cis isomer, where it's kind of the same side, or Z. So then to name these, so this would be trans 2-butene. So still 2, but right, trans again showing how the arms are versus cis 2-butene. And then our alkyne, so now our ine is for indicating a triple bond. And so let's draw out one propyne. So then we have our triple bond, CH3. Oh, and then, right, another way to write this would be like so. But sometimes, again, this can look funny, so make sure you count your carbons 1, 2, 3 properly. So it looks a little funny there. All right, let's see. Wanted to practice some naming. Let's try this tricky one. If I could draw it out properly, that is. Ah, I feel like I got off my carbons somewhere, but I think it'll be okay. All right, so we'll keep it moving, but I kind of tried to draw it deceptively on purpose. So finding our longest chain was actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I was kind of mean. But again, that's like pretty typical of OChem and what you'll find. And so let's try to name all the pieces. So let's see, we got a methyl group, 2 iodos, a chloro, right? So alphabetically, chloro is probably going to go first, right? So it's saying like we alphabetize. And so let's do that. So then we have 7 from our chlorine there. So 7, chloro, then 9 for iodine, right, is next in line, alphabetically speaking. 9, and then there's 2, so di-iodo. And then methyl group is left. So 10 methyl, 3 for our alkyne, so 3. And then we have 12, so dodecyne. All right, so that was, like I said, probably a little trickier than we'll see, but good to prepare for OChem. All right, I know we only have like 5 minutes, so we may come back to this or so. So just looking at our reactions of alkenes, then I'm just trying to think how we'll test over it too. Because like I said, I don't want to get too deep, but we're trying to like expose you guys to OChem because I don't want you to be overwhelmed in OChem. And so our alkenes have a few characteristic reactions. And so typically we see this hydrogenation reaction. You may do it in OChem. It's a pretty common reaction to do. And they make like literally special little like strips of paper that are for hydrogenation and some sort of catalyst. Palladium platinum catalyst is typically used, and again, pretty common reaction to do in OChem. And then you would filter off your catalyst, collect your product there in lab, and again we can see it's just adding hydrogens, so adding H2 right across this double bond there. Similarly, you could do a halogenation reaction, so another pretty common OChem reaction that you see. So in this case, your chlorine or other sort of halogen is added across the double bond again. And then this uses dichloromethane there. So I'm curious what kind of solvents they may have to substitute in for now. And so then this is also what I mean that like, okay, we have to think in stereochemistry all the time. And so thinking about this, and we could even look at the mechanism. And so now we see that this gives us what's called anti-product, where, right, your bromines are complete kind of opposite. And then notice, right, you're going again from a 2D to a 3D structure. And so you'll see this in OChem again, but like I said, good to at least start seeing it now. And so again, you're thinking in 3D. This is flat. Now this bromine can attack from either side, so it doesn't matter, right, top or bottom. And then we make, this is pretty famous, again, in OChem, but now we make our bromonium intermediate, right, where we have this weird bromine positive species. So now bromine's bridging there. And meanwhile, we've created this bromide, and right, very electro-rich here. And so then it wants to reattack this. And so then you can see the arrows kind of showing you what happens. So if you form a bond here, that breaks that. Otherwise, you form a bond on this side and it breaks that bond. But either way, it leads to the anti-formation, which in this case, right, gives you one product. But this is where I'm saying, right, that like you always have to watch out with OCHEM because you're always thinking, will I get one product? Will I get two products? Right? Will I get a mixture of stereoisomers, which of course is a big part of like drug development as well. And what happens when it gets in your body. And so to that point, right, so looking at our E versus now our Z butene. So looking at this, now we could get a racemic mixture from that anti-addition there. And so now we have, right, two different products just because of the stereochemistry of our starting material. So we're not going to like test in this detail probably. That's not my intention, but again, we're still like just learning, being exposed to these reactions, and starting to see the importance of thinking in 3D. And again, going through the mechanism, so we still have that same bromonium ion, right, still forming in the anti-direction. It's just, again, based off of our starting material, we get this racemic mixture here. And so other kind of typical reactions, I know we're probably running out of time, so might save this either with our other OCHEM chapter. We'll see how we shuffle things around. But again, just kind of appreciating that we have a similar bromonium intermediate here. And then depending on which way the hydroxide finishes, right, we get, again, a racemic mixture of products. So just note that, kind of, right, start rotating in your brain that, yes, they are different. And so same thing here. So we'll probably stop here in the interest of time. So we'll pick back up at some point, maybe again coupling with our organic chapter. I was just pairing this. And then next week we'll switch to transition metals, and we'll see when we can revisit OCHEM. And then otherwise I'll see y'all in lab for makeups, or if you just want to hang out and catch up on anything. And I'll watch the chat too in case there are any questions.